Good morning, everyone. So, my name is Emilie Perrott. I'm head of technical department in French Polar Institute. I'll present to you today a project that we have now started for, well, it started in 2018, really, even if some previous studies occurred in 2010 and around. It's about the Concordia solar array and the solar energy potential in the Domsey site. So just a few explanations about geographical situation of Concordia station. So it's the Italian-French station on the high plateau of East Antarctica. It's 1,000 kilometers from Mario Zucchelli station and Dumont d'Urville, which are on the coast. And the latitude is 75 degrees south, longitude 123 degrees east. So it's obviously there is continuous sun in the summer period, but no sun in the winter. So there is solar potential and interest, but not to cover all the year, at least not in an evident situation. There are very low temperatures there, minus 30 average for the summer temperatures and minus 60 to 70 for the average winter temperatures. As I said, it's on the high plateau, so it's on a very high level of 3,000 and 200 meters. And the pressure there is quite low, 660 hectopascals average. There is not, it's not a very windy region, so, well, we'll be talking about solar potential today. We kind of let wind potential aside. This is not really sufficient. There are sometimes a few windy weathers, but not to exploit anything. So Concordia facilities. Well, there are two main buildings which we call the towers and the power station. The main buildings are 1,500 square meters. And the station runs almost, it runs on the diesel generation power. We have 3 engines. There's only one running at a time on the normal operation situation. So this is a typical annual electrical diesel production in Concordia station. So you can see that we clearly identify the summer period, which runs from the end of October to the end of January. And there is a peak where the average consumption of electricity is around 2,700 kilowatts per kilowatt hour. And in winter, it's more 2,200 kilowatt hour per day. So this is the period that will interest us, the summer period. Now, about the site and the solar potential. So the sunlight exposure of Concordia, the sun doesn't go very high in the sky, obviously, but it produces, in summer, it produces from all directions. This is a small chart that shows the solar radiation on an horizontal plane, the floor, which is the blue columns, and in the collector plane, if you follow the sunbeam direction, which is the yellow one. What is interesting to see is that in the mid-season period, there is clearly a difference between the horizontal plane and the collector plane, which is something we might want to exploit. This is a sun path chart in Concordia. What I wanted to show here is that so the maximum height of the sun in Concordia will be 38 degrees on the 21st of December. So this is to explain how we choose to orientate our panels, because we want to maximize the energy that we receive from direct solar radiation, which would tend us to incline the panels on a more horizontal tilt. But we also want to beneficiate from the snow albedo. So we don't want to put them too horizontal because we won't beneficiate from this albedo. So there were some calculations made, and the orientation we found was 75 degrees. It's funny to notice that it's very often the optimum orientation is also linked to the latitude where you're situated. But anyway. About the design of the solar panel support, so the optimum tilt, we just talked about it. Then we wanted to exploit different orientations and keep some maintenance space. We wanted some simple support structure, which is quite easy to manufacture and assemble on site. So that brings us to this A shape, where we put 24 solar panels on each side. So one support is 48 panels in two directions. This is one of them. And then we thought about different spatial layouts for this support to make a solar array and to exploit all four directions. So we thought about a swivel holder, which would turn and follow the sun course, and 5 different fixed layouts. So I will go fast on these kind of slides, but if you want to check them afterwards, you can. I'll just summarize. We went with the 4th layout, which is not the most efficient one, but it's the best compromise between the investment cost per kilowatt hours and yeah, it's also the swivel holder obviously is very interesting, but quite hard to manufacture and operate. So we went with the fixed holders and chose the 4th layout, which is just this one on the slide. So it gives that. So then one layout, one full set is made of 3 supports, so 144 panels. 48 are heading to the west, 48 to the east, 24 to the north, and 24 to the south, which can be quite surprising, but we'll see that it's not that useless as we could think first. So this is the photo. And then for the results, so we've been installing this support. The first one was in 2000, well, it was summer season 2021, and all the full set was assembled during 21-22 summer campaign. So we had 1 full year of operation. Production for 1 year is 62.5 megawatt hour. And what's interesting, this chart shows the production for each month of the year. So production starts mid-August and ends mid-April. But what's interesting is that even the south side is producing energy, which is probably mostly due to snow albedo, but we shouldn't neglect the north-facing panels. This is the same chart, but on a daily basis, where you can see cloud impact, but Concordia is quite favorable, very good weather there. The sky is often clear, so it's not impacting that much the production. This chart is showing the power during one day. So there's an error on the slide that I will correct between east and west. But anyway, you can see during the hours of the day which side is producing. And the blue curve is the total power during the hours of the day. So back to the first chart that I show. This is still the annual electrical need in Concordia, which is 821 megawatt hours. And then with the solar production, which is in green there, we can see the now resulting diesel power generation. So it's not that impressive, but still. It's a start. What's very interesting is that on the 144 panels that we installed, the calculated theoretical annual production was 51 megawatt hours, sorry. And we reach more than that, 62.5, because the conditions are optimum there. The temperature is very low. The albedo is some like free energy that the industrials wouldn't count on it. Also, in the calculations, they consider some cloudy weather, which are not that often. So there is like a bonus annual energy of 11 megawatt hours, which is very interesting. This is the fuel that we saved over a year, which is 8.4% of our consumption for electricity production. And just changing the panels, because the progress in that field are going very fast, just changing the generation of panels on these supports would lead us to 13% of savings. So it's interesting. But it gives a lot of other ideas, which we can consider for evolution extension philosophies. The first one would be to just complement diesel production, but not go over this 30% limit of charging our diesel generator, which is a limit where they're not operating that efficiently. It wouldn't impact the operation of diesel generators, but it's not maybe that interesting or that challenging. I won't go further into that today. The number two solution would be to produce more energy with the sun, but then to go over this level of 30% diesel generator charge. But that would require energy storage if the sun is the production of solar energy is stopping for any reason. It brings complications. What is interesting to consider could be to produce enough solar energy to completely shut the engines in the summer period. It would require maybe 1 day of storage to be able to cover a cloudy period. But for the diesel generator functioning, it would be more reasonable. And then there is the fourth one, the dreamy one, which would be to go over the winter period with solar energy. But I won't have time to go into that today, I think. But it's funny to study anyway. So this is just if we invest in some more sets of panels, the same as we first developed. This is just showing that with 4 sets of panels as the one we already have, and a change for more efficient solar panels, we could reach sufficiency. We could meet the electricity need in summer, which are the green cases. This is a chart showing the same thing. These are the different production with the solar energy according if you put 1 set, 2 sets, 3 sets, etc. Maybe the safer coverage would be with 5 sets and a short storage for 24 hours. So this is maybe the thing we want to aim. I won't go too much into that, but these are some calculations about the storage that we would need. What's interesting to see is that if we're talking about 1 hour storage, this is still quite reasonable, the weight of the battery bank, the cost, and if you want to cover a few days, it starts to be very ridiculous very fast. And so that's it for the number 3 scenario. And just for the fantasy number 4 scenario with storage to cover also the winter period, which is interesting is to see, so hypotheses were based on hydrolysis of hydrogen, compressed hydrogen. It's just to show that the needs that we have in winter are around 350 megawatt hours, and the energy we would have to produce to store it over the winter would be 989 megawatt hours. So it's quite big, and I won't go into that table today, but these are some fantasy calculations about the number of cylinders we would need to store such a quantity of hydrogen, which is quite big. I've finished. Do you have any questions?